Good evening. So this is a talk on Meso-scale assimilation and prediction of extreme weather events over India. So this talk is, though I am presenting, it is a work of my young colleagues and students, and few of them are here, like Krishna, Sudhata, and few others. So in this talk, I would like to give an outline of my presentation, that I will give a brief introduction of the built modeling systems and particularly the data assimilation. Then under extreme weather events over India, of course there are many extreme weather events, but I will focus mainly on severe thunderstorms, heavy rainfall events associated with monsoon and western disturbances. And tomorrow I will cover on tropical cyclones over the Indian seas. And all these activities done with Meso-scale models. Particularly we use advanced WRF, that is ARW, and NMM WRF, which is operational transect, and also some of the results on a hurricane work, which is research version of hurricane work and hurricane research division, NOAA. So these models are adapted from NCAR and NOAA in India, and extensively work is carried out on particular data assimilation, which is very particular for this region. And so therefore I will show you in this mainly that the performance of these models and in particular the data assimilation. So as you know that the extreme weather events are the very short-lived events, and obviously they are the initial value problems. And numerical weather prediction, therefore actually when you go to numerical weather prediction, it means short or medium scale predictions. They are the initial value problems, and they have therefore a limited predictability, and that scale depends upon the consistency and quality of the initial conditions that is put to the model. And as you know, in the recent years, there is a lot of improvement in the numerical weather prediction models. That is because of the increase in the model resolutions. And now you have seen in global models also, which is 3 or 1 kilometer is possible. Improvement in physical parameterization schemes, and in particular in the tropics, it is very, very important because here the physical forcing is as large as of the dynamical forcings, and enhancement in the observation networks and availability data from the various non-conventional platforms, and in India it is particularly from the Doppler weather radars, and of course we have only one profiler from upper observations currently only, but there is a plan that we will have many profilers, but we have a large number of Doppler radars now deployed in the coastal areas, and particularly the region where we have the severe thunderstorms and tropical cyclones. And improvement in analysis and assimilation of this type of data in the models, enhancing the computing facility now has helped to go higher and higher resolution. So as I told you, these high impact weathers, being they are very short-lived, fortunately, and they are very high resolution because they are the convective, tropical convective activities, as you have seen the early morning faster. So therefore, we should have a high spatial and temporal quality of observations, and in that the weather radars, specialized satellites, like we have the tropics and so on, and micro radiometers and profilers. They are very, very important to give more frequent observations to study such phenomena and their data assimilation. So therefore, if you see the essential components of a deterministic extreme weather events, prediction So, of course, dynamical framework, which we have a lot of discussion and presentation since today morning, that is one of the main thing. In addition to that, we understand the extreme weather events, and it lists parameters of physical processes, data assimilation, where initial conditions like observations, assimilations, and the installation of the system, numerical solutions, and finally, after integration of the model, its application. In the application, starting from post-processing and validation of the forecast models, and prediction of non-conventional variables like thunderstorms, it will not come exactly in the model as a parameter, like basic parameters, but it is derived. And similarly, visibility or fog and so on, and forecast errors, statistics, and bias corrections is one of the another aspect, because each model have its own bias in a different region. And obviously now we all are moving from single deterministic model to probabilistic model, where the prediction is probabilistic in nature instead of a single deterministic forecast, and it has more durability of application, because people can know that what is the probability of occurring, or what is the chance of occurring. So therefore, successfully forecast requires initial conditions that are adequately represented with the state-of-the-art atmosphere in three-dimensional, wind, temperature, pressure, moisture, and its different phases. And then high resolution data assimilation with sophisticated data assimilation schemes like variation data assimilation and ENK. In tropics, wind and moisture, they are very important compared to other parameters, because they are the mainly responsible for the convergence process and initiation of the convergent activities. And you see the names of the different observations with the different platforms. So when we come to, I will not go details in this 50 minutes, the details of the data assimilation scheme, but as you all know that the scheme actually it needs a background pre-processing to get background error statistics have to develop for the model, and then it can run as a cold start, and also it can run as a cyclic. And we have done several experiments, and we found that cyclic is much better than to have a cold start. In cold start, you take a initial condition from some of the model like GFS or any global model, and take as an initial condition and background field, and then you make a cold start with taking the observations and taking the cold start model from the FNL, GFS or anything, and then run it. But then those models are obviously have different physics and different resolutions, and instead of that, if you take actually few hours, few days or few days before the start of the analysis, if you take the same Meso-scale model, 6 hours forecast as a first guess, and introduce the observations, then it became a that is a cyclic where you get the background fields from the model result, and then once you make assimilation, the forecast can be made. So if you see the natural hazards, this is the report of WMO for the decade for the disasters, natural disasters. It found that hydrological disasters, which mainly cyclones, floods, droughts, tornadoes, thunderstorms, heat waves, and so on. And whereas another disaster, geophysical disaster like earthquake, avalanche, landslides, and so on. So this shows that in these 10 years, if you see the blue one is the hydrological disasters, and that one, this one is the geophysical. So this shows that the hydrological disasters much more numbers than, and intensity compared to that of the, and more than 90% people killed by meteorological and hydrological hazards. That is the report of WMO. And similarly, if you measure disasters around the world, then we see that the drought, tropical cyclones, earthquakes, and other disasters. This is the distribution, significant damage due to disasters. Again, tropical cyclone, flood, and drought, they constitute about 80%. If persons affected, you see also drought, tropical cyclone, flood are the major disasters, and that is due to extreme weather events. And this is an interesting one. If you see total number of reported disasters, then Asia is only 43, America is 23%. But if you see the total people killed by the disaster, then Asia region contributes almost 80%. And Asia occupies about 33% of the world land area, and accumulate about 61% of the population, as you know, like India and China is highly populated. So in that aspect, and this is mainly actually attributed to that many countries in this area is the developing countries, and where a warning system and mitigation strategies have to be taken up more urgently or more required, so that otherwise this is the ratio it shows that like 2005, the 25 hurricanes were there, only 12 people died in USA. And whereas we have a cyclone like Nargis, where about 1.3 lakh people are perished in one cyclone. So similarly, this is global impact of natural disasters. That also shows that the hydrological disaster is about 77%, and that is it. And similarly, IPCC assessment. So this is, I took from IPCC report from 20th to 21st century to see it is projected that all these type of natural disasters like tropical cyclones and intense precipitation and so on, they will increase about twofold. So this is a projection only, but it has a impact obviously on the people, economy, systems, property, and ecology of the region. It is a work by Matt Dean in Nature 2005. So this shows that the importance of the extreme weather events which have a high impact in the society. And in our context, these are a large number of weather and water and climate related extreme weather events. As I told you in the beginning, I will focus on these three aspects, and I will start with this one. Do you feel or not? I'm going to see it. So I start with the severe thunderstorms. In that, actually, I will tell very briefly the climatology of the severe thunderstorms and its application of air model and the different initial and boundary conditions. I will show you also impact of the reflectivity and the radial velocity assimilation of JWR, impact of radiance, satellite radiance assimilations, and in particular also land surface data assimilation based on surface conditions. If you see that thunderstorms activities, so this is mainly actually northeast part of India, that is, and Bangladesh, Nepal, and Bhutan. So this is the area which is affected by severe thunderstorms. Though actually the whole country have severe thunderstorms before the pre-monsoon period, that is the month of April and May, but this is the region where you get maximum about, in these 2 months, the period, about 120, sorry, this is the annual, 120 you get thunderstorms, and you can see each of the region there, we show that the maximum thunderstorms occurs during pre-monsoon and monsoon period. Similarly, these severe thunderstorms are associated with hailstorms, and during the last 100 years, it's statistics show that about 100. And this is one of the areas where we get a large number of hailstorms associated with severe thunderstorms. So if we see monthly frequency of these events, the diagonal variation, the monthly frequency, then you can see that this is the peak, April and May here, and it's decreased. And similarly, if we see that the diagonal variation, then it mainly occurs generally in the late afternoon or evening time, about 17 hours, that is local time, that is about evening 5 to 6, that is the period when it occurs. And in fact, actually, if you see the whole region, so early morning time it occurs over the head bay, and in the daytime as moves, it is built up over the land. Similarly, the frequency of the tornado, this occasionally the tornado also associated with the severe thunderstorms, and that will occur more. Again, this is a record for this 1839 to 1999. So of course we don't get so many as in the USA, but here about 25 is the maximum in April, and May around 14. And this is the region which is mainly affected by the tornadoes in India. This is a report by Sahan and others. And therefore, actually, we have we made a program, storm program, severe thunderstorm observations and modeling in this region, a field experiment, and now this experiment is converted to a multinational experiment involving SAARC countries, and the one we are conducting here, that is with Bangladesh, Nepal, Bhutan, and Northeast India. And this is one of the reports. It shows that most of these severe thunderstorms, the direction of movement, they come northwest generally, and that's why we call them also other known as northwesterly, northwesters, and in local language it is also known as Kalbaisaki. So here actually what happens, the severe thunderstorms thunderstorms occur over the ocean area in the early morning, and in the day as progress with cities, then the things that the moist air moves from the ocean side towards land, and at that time in the foothills of Himalaya, then they are developed and they move towards from northwest towards the southeast. So this is one typical Doppler radar picture of a one day of the, that is 11th May. So these square lines, this is the Doppler radar at the Calcutta. So I will show you some numerical modeling experiments in this, and the model configuration is the WRW model, which we have taken actually single domain with 3 kilometers resolution, and it is integrated over the region. Then I will show you a few typical cases, that is a squall passed over the Alipur, 50 km per hour, and lasting for 1 minute, and similarly after the Dum-Dum. And synaptic situation for that is that the upper air cyclonic circulation is in low level over the north Chittagong and neighboring areas, and the upper air cyclonic circulation low level over Assam and neighborhood, and then there is a jet core running along the 28 degree north. And so here actually this is the one which is observed from the Doppler radar, and this is one where actually the FNL analysis has taken as initial conditions, and here it is taking GFS, and which initial and boundary condition from the GFS output. So if you see that these codes, they are well simulated by both these initial conditions, and this is the surface pressure, and this is time of occurrence, and here observed FNL GFS, and this is 2 meter temperature, here if you see GFS assimilated very close to observations than that of the FNL, and this is of relative humidity and wind speed. And this is the cape associated with this severe thunderstorm. And this is the precipitation. This is the observed one, the black one, the red one is the FNL, and the green one is the GFS. So there is a 2 hours before it occurred in the GFS, but obviously GFS was much closer to that of the observations, the amount and the intensity compared to that of the FNL. And this is the vertical velocity. Same way also, you can see that the vertical velocity is quite strong and in the GFS. Then we use the Doppler radar data and the satellite variance, and I will show you two experiments with the control without data assimilation, that is FNL, and DW assimilation of radial velocity and reflectivity. And this is the severe thunderstorm of 12 May 2009. So this is a satellite image animation of the thunderstorm event on 12th May. You can see that the temperature was -75 degrees centigrade. And this is the wind at 850 HPA at the control, and this is DWR minus control, and the specific humidity. And this is the control line, and this is the DWR simulation reflectivity, and this shows that it's more intense in the DWR, and this is the cape and sign, and this is the lift index. Though they looks almost similar type, then you can see the relative humidity. This observed one, and the blue one is the DWR, and the red one is the control. So both show that there is an increase of enhance of the relative humidity, and this is the precipitation. But here again the DWR so close to that, but the thing that that time DWR is taken only 6 hour interval. They are scanning. That's why we got only we could not make a 3 hourly assimilation if we done only 6 hourly assimilations. And this is the trim, and this is the Doppler radar Calcutta. This is another location where we have the many observations we are taking, that is IIT Kharagpur. And this is the water trim observations, this is control, and this is water DWR simulated. And this is the specific locations, and this is the observed specification, this is the control, and this is the DWR. So you can see that the DWR looks closer to the observed compared to that of the control. And same thing I put in the histogram form. And the studies show that trim data actually they cannot really show that type of high intense short period rainfall so well. So therefore correlation is quite less compared with observations, but the DWR shows about 0.87 correlation between the observed with that of the simulated one. Similarly, we have done the impact of satellite radiance assimilation and severe thunderstorm simulations. So for that squall, we have taken actually of 70 km/h, lasting for about 2 minutes. That was recorded at one of our observatory at Alipur in the DC in Calcutta, and that is on 31st May 2011. And the same squall is observed at different points at different time. And here I will show you some results with the control without data assimilations, that is FNL. DTS assimilation, DTS observed using WR system, and satellite radiance assimilation, and satellite plus DTS. So this is a satellite imagery for the 31st May. This is the squall that we passed through this region. So this is the distribution of the data for that case, different observations, and this is the satellite radiance data that we use. And this is the tape, and this is the lifting index. So this shows that we are going to have a thunderstorm occurrence about 10 UTC. And this is the data values of the temperature, and this is the accumulated rain, and this is what we observed. So here again you can see that when we have satellite GTS, that is little better than other two, and this is the 3 hourly, 6 hourly accumulated rain. This is the control GTS, and the last panel is the trim data. So here you can see also, so it occurs between 12 to 18 UTC, and this is very well simulated with satellite plus GTS. And this is the, we calculate the height skill score for 3 hourly accumulated rain. This is the control GTS satellite. So here you can see that it's larger than compared to other. ETS also more than 0.2 on the satellite. And there is scope for doing the multiple radar, because this is only one radar we have taken that time, and that is available now. Another 2 radars have come at Patna and other place. So we are working on the multi-radar data assimilations, studying of the impact of the land surface data assimilation. Of course, we have done something, but I don't have enough time to go through that. And impact of urbanization on thunderstorm is another important aspect, because it is in that the certain part of the city you get more thunderstorms, severe thunderstorms compared to other part. So urbanization is one of the important aspects that we land use land cover. That is what is very much important also in the simulation of these type of thunderstorms. Then I will show you our monsoonal heavy rainfall events, and one case of the western disturbance also with the same ARW systems. Here actually impact of DWR data assimilation on monsoon depressions, because most of the time the heavy rainfalls are associated with the monsoon depressions. And you may be aware about Bombay heavy rainfall events, where actually about 94 centimeter rain was there in 24 hours. So it was a case where about 300 people were killed in that Bombay heavy rainfall for one day. And the impact of land data assimilation on monsoon depressions and western disturbance and associated precipitation. So here actually I will show you a few cases. 5 to 7 July 2007, 2nd to 4th August 2006, and 21 to 23rd June 2007. So this is the associated with synaptic situations, genesis over the West Bengal, moving completely with the westward directions. And second case also, which along the coast of India due to lift of depression over the Bay of Bengal and extremely heavy rainfall over the eastern central part of India. And third one is along the east coast of India again. So this is the data of DWR Calcutta taken. And this is the 57 July 2007 monsoon depression and associated rainfall. This is a patient and model observed. rainfall, this is the control, this is the GTS alone, and this is the DWR plus GTS. So you can see that DWR plus GTS, the simulation is quite good from as that we observed, which is fell control run, and this is the ETS of the case 2 and case 3, that ETS of rainfall with the different threshold values, and here you can see that in all ranges of threshold, the blue one is higher than other two in both cases, and that is where the DWR data is used. And this is all the three cases of RMSE and correlation. So if you see control versus ETS plus DWR, then there is a 0.25 against 0.62, and 0.3 against 0.77, and 0.37 against 0.74. So that we can see that if you include the weather observations and assimilation, then there is a quite good improvement in the precipitation. And similarly, this is the mean sea level pressure. This is the second case, and this is the RMS of the mean sea level pressures control, DTS and DWR. So here you can see control is 6.5 hectopascal with the RMS error, but it is reduced to 2, so that means intensity is very well also simulated when you add this Doppler weather reflectivity and radial velocity. Similarly, from control 4.3 to that of the 2.1 in the wind. And this is third case, again 5.2 to 2.3 and 3.7 to 2.7. So this shows that it is almost the intensity is very well simulated compared to that of the control data. And this is the track of the depressions, 57 July 2007. So here, black one is the best track observed because it is over the land. The entire genesis is here and it moves over the land. And the blue one is the control, and the red one is the Doppler radar and the DTS data. And this is the vector displacement errors. And again, the blue was the control and the red one is the Doppler radar. So if you see that in all the cases, there is a substantial increase, reduction of the errors, and in fact, if you calculate the percentage wise, about 40% implemented there if you take DWR plus versus the control. Similarly, this other one, 2nd to 4th August. Similarly, if you see that, so here again, the black one is the best track of the observed track of the monsoon depression from 2nd to 4th August. And here, this is what is the control one, and of course the initial position was quite large. And then this one is the only GTS data, and the red one, where actually DWR data with GTS, and this is used. So here if you see that the vector displacement errors, and then this is the control at the initial conditions, so it is quite away from the actual positions. Actually, this is displacement is quite large initial time, and this is the GTS, and the red one is the Doppler radar. So if you see for 48 hours simulations from 2nd to 4th, then you can see that in all the time the one with DWR data, the error is substantially reduced compared to that of the control. And so this is the GTS versus control is 35% improvement, DWR versus control was 69%, and DWR versus GTS is 54%. That means DWR plus GTS versus control is about 70% improvement in the track in this particular case. And here all the assimilations we have carried out in 9 kilometers and model is simulated in 3 kilometers. So this is similarly another case, and there also you can see also this is the black one again, same color code. The black one, the upper one, and the red one is the one where the GTS, DWR, all the data is assimilated, and the blue one is the FNL data. And this is the, again, vector displacement errors in all those cases. And here you could see that control versus DWR for GTS, again around 50% improvement is there in the assimilated, the simulated track compared to that of the control graph. So all these 3 cases will demonstrate that there is improvement in the simulation when you add the parallel reflectivity and radial velocity. So similarly, I will show you the impact of the conventional data assimilation on Bombay rainfall which was 26 to 27 July 2005. In this case, actually, as I told you that there is 94 centimeters there, the rainfall within few hours of a day, and it is the whole city actually was almost standstill, and more than 300 people are perished. And that is such a Meso event that one side here, that is Santa Cruz, which you have a 94 centimeter, and other side about I think 30 kilometer aerial distance, it was only 10, less than 10 centimeter was the precipitation, and this is the city of Bombay, and of course these are different locations. I will not go through the details. So, and this is what was seen from the TRIM data, and so this domain is we are showing the domain 1 is the 30 kilometers, and domain 2 is 10 kilometers, and here actually I will show you the 2 runs, vertical level of 51 sigma levels, and control versus 3D work. So this is the data coverage that is taken into account for this one, and this is synapse, and this is the soundings, and this is pilot, and the quick start data we have taken, and the GTS satellite data are taken, and this is the mean RMS error. Here actually I am showing from analysis. So the blue one is that where actually we are doing the cyclic data assimilation, and the green one where we are taking cold start. So I was telling you that beginning the cold start versus cyclic. So that you can see in all the cases of lunar wind, nominal wind, temperature, and humidity. In all the cases, the cyclic is better than the cold start, and the pink one is the FNL. So which is the RMS error is the minimum when you are taking the cyclic conditions, and it is throughout the atmosphere that the increase of, there is a reduction in the RMS errors with data assimilations, and this is the 24 hours. Mainly RMS error after 24 hours forecast against verifying observations, three sets of experiments, and again in all the three cases the general wind, vanilla wind, temperature and Q, you can again similarly you can see that there is a reduction of errors, and similarly you see against the FNL analysis, verifying FNL analysis. That previous one is the with the IND RSRW observations, and this is against the FNL analysis. So you see that it will be much more improved. And then this is the observed and simulated 3-hourly interval cumulative rainfall. So here actually this is the observed one at Santa Cruz, the black one at the top. The dashed black one is the Colaba. So I told like two sites in the same city. And one has about 94 centimeters, almost 1 meter precipitation in 24 hours, and other one is about 10 centimeters. And this is what the control run, the green one and the blue one is the 3D assimilation. After that it is integrated. So in both the cases, this type of Meso-scale events which are quite well simulated, though it is not exactly the same, which is not possible, but then it is simulated about 78 centimeters, and the other place also about 10 centimeters. And in both the cases, the assimilated run, which highly assimilated run, shows the better simulation compared to that of the FNL analysis. And then this is the 3-hourly accumulated rainfall, control, 3D work. And then we try to see the cloud microfreeze, and it is found that it is 3 cells are passed through that region with time, and the rainwater mixing ratio and the surplus pressure which is depicted here, and you can see that the first one contributed about 222 millimeter, second cell was 216 millimeter, third cell was 111 millimeter, and that is what is contributed to us that 78 to 79 centimeter rain in 3 spells by passing through 3 cells which is not really simulated with the control one, but which are all simulated with this type of assimilation with that of high-use model. So similarly, this model simulated vorticity and vertical velocity. This is the control one. Vertical velocity is 74, whereas it is quite large in the 3D work, and similarly it is the vorticity. So this low level from vorticity is almost absent in case of a control run, that leading to that type of large scale vertical velocity and having that type of severe convective activity there. And this is the simulated rain. 24 hours accumulated, this is the trim, and this is the control, and this is what the 3D simulations. So it could have well simulated this type of 3D rainfall. Then I show you the impact of the high resolution land data assimilation. So here we are using LDAS systems, and this is there, and this is the configuration of the land surface data assimilation scheme. This is the domain, and we have taken the NUHA scheme, so the core layers same as the NUHA scheme that is taken, and for the dimension of the this thing one-dimensional LDAS system is used, and for this we have input we have taken mirror data, and which is available at 1 hour interval. Of course, it is interpolated, and we initialized the model from 1st January 2006 and integrated it up to 30th September 2012, and the span of time is about 6 to 9 months for this experiment. So this is the model domain because I want to show the simulation of the monsoon depressions. So in this case, actually the source of data is the mirror. This is the flow chart of the L dash. So we have taken the rainfall from tree and initial fields, and we have taken mirror, and then this is, we try to see that with tower data available at 2 points. One is the Kharagpur, IIT Kharagpur, another is the Ranchi. So here actually L dash moisture, soil moisture, and the red one is the observed soil moisture at that location. And these are the rainfall reports, but this rainfall is not taken in the model, it is observed. Rainfall we have taken actually, as I told you, the 25 kilometer trim data. And but you see that most of the reports, you see that it is associated with the rain, and this is the another site, Ranchi. So this impact of L dash by soil moisture that we have obtained from this was used for the integration of the model with the same cases, and we have taken actually 8 cases in that, but I will show you only. One in the 2007 and one is the recent one 2011. So this is the object track of 8 monsoon depressions for which we have carried out this experiment. You see the impact of the land surface data. One is the control, other is the L dash. So I have to pass to quickly. This is the soil temperature, control L dash and L dash minus control. So this shows that there is a lot of difference there in some regions. And this is the surface net radiation at Kharagpur. Again, the control shows quite large value. And this is the black one is observed, and this is the blue one is actually the L dash. And similarly, this is another case of same place. And this is the model simulated track. Here actually in all the cases, black one is again observed, blue one with L dash as an input, and the red one is the control. And these are all 8 cases, the track, and if you see the mean track errors, again the separate one is the control and the blue one is the L dash, and this is the mean position errors of those tracks, and this one is the percentage improvement, 30.6 hours to 72 hours the model is integrated. So this shows that there is about 30% on the average the improvement is there. If we take instead of USGS data, which generally we use as a control, versus the data that we have generated with the LS system for that 5 years integration. And this is the precipitations, cross sections, time versus latitude. Again, you can see that this is observed, L dash and control. So this is all simulated here. This is model simulated precipitation again. I will go through very quickly. This is also, we have tried for this in there is another cases of 2 cases of heavy rainfall in Delhi. And here this is observed, and this is L dash, the red one, and the green one is the control by the USGS. And that's that I taken. The rest of the things are same. Again, you can see that this is hourly rainfall. So this again clearly also show that by making a realistic land surface data, it improves the simulations. So this is the conclusion. Statistically, what it can be further improved because we are using mirror data, and I don't know how many observations coming there is going there, but that is a consistent one. So we are now trying to that we have a large number of AWS and automatically engaged in the country. So it is we are trying to get the data and assimilate that at the surface initial conditions, because which those are the initializing the system, and the rainfall has significant impact in the soil moisture and soil temperature, so that you need a high resolution and the true data. As I told you, that the best data is available, but still then it cannot represent the heavy rainfalls. So this is our future direction. That's where we can use the Indian observations and make a assimilation, and use that assimilations to initialize the oil gas system, and then also from satellites, the land cover data is available that can use, and soil category and soil vegetation, which can further improve this thing. I think I will stop here.
Thank you. Okay. Any question for Professor Mohanty?
Yeah, I'm an outsider, but what we see from the daily predictions of the weather in the television and also the monsoon, what happened last year, there seems to be a lot of issues. We are not able to do good prediction. Can you please comment on it? I mean, your talk looks, your data looks nice, but on the whole, what goes wrong?
Yeah, you said I should not, because our friend tomorrow he is coming, actually, Dr. I Bhavin from Indian Meteorological Department. Actually, so I should not comment on that, but they have not used till now. They have not used their operational suite of the Doppler radar. It is just now they started with the apps model in few places, and unfortunately the best person, but they have not assimilated those data, and that will be one of the beginning. Maybe because that data assimilation they have to improve, because these are the short-lived cases and they need a better assimilated data. That may be one of the beginning. And of course, what we are showing, except tropical cyclone case, which I'll show tomorrow, that data we give to, we predict also tropical cyclone in real time and give to IMD along with their operation. They use our prediction, but these things actually we don't pass on to them. But I think they are in the process to improve their system, and for which they are working. So I think he's the right person to comment on this thing.
Which is, according to you, is the best model to kind of learn and use among what is available right now?
You said best model, you said which model is best to tell is a million-dollar question. But generally, actually, we have seen that if you take a high resolution Meso-scale model, particularly WRF, and because we have seen that the approach cyclone, we have seen that the NMM WRF and HOR, that doing it better. But still then actually it is very difficult to tell which WRF model is better, but WRF model with high resolution, with better data assimilation, it is improved substantially in this region, because we have very less data, and FNL, I don't know how much data goes from India. So if you put Indian data, and particularly to this type of Doppler radar and all these things, it improves even thunderstorm or this heavy rainfalls and monsoon depressions, and I will show you some cases of tropical cyclones. So there is a lot of scope in this region to improve with high resolution Meso-scale model with a better data assimilation.